Hello everyone, I am Bhupesh Kumar. Right now I am working as a postdoctoral researcher at the University of St. Andrews. I want to thank the organizer of the conference who invites me to give this presentation. In this presentation, I'll give a brief review on random ledgers. I will start with brief introduction to random ledger, I will talk about brief history of random ledger, classification of random ledger based on feedback mechanism in coherent random ledger and coherent random ledger. I will discuss random ledger in different gain medium and future possible application of random ledgers. Ledgers first demonstrated in 1960. As we know, essential component of a conventional lasers are pump source, gain medium and a cavity that is composed of a set of mirror. One is fully reflecting and other one is partially reflecting. When the gain medium is pumped, the role of the cavity is to provide optical feedback and also determine the directionality and mode of the laser. In 1967, V.S. Lethokov, a Russian scientist, published a seminal work where he proposed that generation of light by scattering medium with negative resonance absorption. Imagine that a gain medium with lots of scatter particle. When the light passes through such a medium, the emitted photons encounter multiple scattering before they get out of the system. So thereby the multiple scattering, therefore the multiple scattering increase the dwell time of the photon in the medium, or the in simple words we can say the time spent by the photons in the medium. So this in turn raises the amplification efficiency of the light. So that means instead of using an additional reflector in the medium, scatterers help to entrap the light. So from here the term random lasing comes, and here the term random medium define the kind of a disordered medium, and the random laser is an active medium with many scatterers. So therefore a random laser is also called a mirrorless laser. However, the real breakthrough in the so-called random laser emission come in 1994 when Lavande and co-worker employed a nanocomposite prepared from a colloidal suspension of organic dye and nanometer size titanium dioxide particle to clearly demonstrate laser emission in a gain medium in the presence of scatterers. For the record, until then, the term random laser had not been used. In fact, when Virsma and co-worker questioned the result of this publication by Lavande and co-workers, in their comment to this publication in 1995, they used the term random laser with a question mark, and the reply given by Lavande and Balachandran providing the clear evidence of laser action, and since then the term random laser was coined. Virsma and co-worker suggested that the underlying physical mechanism in random laser was not true laser coherent oscillation, but it is an amplified spontaneous emission ASC, which does not require a cavity. However, Lavande and Balachandran rule out the possibility of ASC emission and show that the scatterers was the fundamental ingredient for the observation of laser-like behavior. Depending on the feedback mechanism, random lasers can be classified into two types: incoherent random lasing and coherent random lasing. In case of incoherent random lasing, wave nature of the light is neglected because interference effect does not manifest in the experiment. The role of the scatterer in this type of random laser is just to provide feedback for ASC, called amplified spontaneous emission. In this case, the feedback provided by multiple light scattering does not return the photon to its place of origin. In incoherent random laser, emission peak is broad and continuous without any sharp lasing peaks. As we increase the pump energy for such lasers, the width of the emission spectrum narrows down, but there are no sharp lasing peaks in this case. In the case of coherent random lasing, the wave nature or interference effects are considered. The field feedback is phase sensitive or coherent, and therefore it is a frequency dependent. This type of random lasing emission spectrum consists of sharp lasing peaks on a broad emission spectrum, like you can see here. The observation of coherent random lasing or coherent feedback by Huikao at Northwestern University in 1999 triggered the story of random laser. She pumped a zinc oxide semiconductor powder and observed first narrowing of the gain curve followed by appearance of sub-nanometric lines in the spectrum, which are similar to real lasing modes of a conventional laser. However, there is no cavity, and question was therefore to understand the origin of these lasing modes and feedback mechanism involved in this type of random lasing. The evidence of interference effect associated with recurrent light scattering in random laser were presented by Huikao later, and who investigated random laser emission in a powder of zinc oxide and gallium nitride nanoparticles. After the demonstration of coherent random laser was demonstrated in different systems. One of the simplest way to construct random laser is by preparing a liquid solution of laser dye which present a large quantum yield with suspended scattered particles. This type of system has 3D geometry, and one can control such random lasers by selecting the scattering particles and density and dye concentration respectively. Titanium dioxide nanoparticles are most used for colloidal random laser because of the large transparency from the visible to near infrared and large refractive index, which provide large scattering strength. This figure here shows performance of dye-based random laser using titanium dioxide particle in both non-functionalized rutile titanium dioxide and functionalized amorphous titanium dioxide samples. Random lasing peak intensity is plotted as a function of the number of shots, with measurement performed at 5 Hz and excitation pulse energy of 4 mJ, which is above the threshold in both cases. The here upper inset shows solution with rutile and amorphous titanium dioxide particles and an empty flask. Beside these titanium dioxide particles, random laser has been demonstrated by using particles like zinc oxide, silica, alumina, tungsten dioxides. Random lasing is also reported in dye circulated structured polymeric microfluidic channel. Several millimeter long microfluidic channel with 10 micron thick PDMS polymer wall was placed periodically with a period of 40 micron was fabricated. Here, structural disorder result from the limited resolution of the photolithography process used. The microfluidic geometry advantageously offer continuous flow of dye which prevent dye bleaching and reproducibility of the emission spectrum as well as local control of scattering property of the disordered structure. When the sample is optically pumped above threshold uniformly along the length of the channel, multi-mode emission peaks appears on a broad background which confirms the random lasing. We have also designed a solid-state organic random laser which provides the benefit of laser emission stability. To fabricate this random laser, a 600 nanometer thick layer of DCM dye-doped PMMA polymer is spin-coated on a fused silica plate. This layer is structured by engraving hundreds of parallel randomly spaced air grooves using E-beam lithography. The control disorder is introduced by varying the groove position around the 8 micron periodic arrangement. A small section of the sample with air grooves is shown by some image here. When the sample is optically pumped, current feedback is provided by 125 parallel grooves randomly distributed along the 1 mm long sample, and resultant random lasing with sharp lasing peaks is shown in the figure here. Now I will talk about random Raman laser. Raman scattering is the inelastic interaction between photon and matters. Random laser emission by using stimulated Raman scattering is called random Raman laser. It can be explored for the detection of chemical components in powder sample. In 2014, Brent Hocker and his co-worker reported the first ever experimental proof of Raman interaction in a bulk 3D disorder medium that is made up of barium sulfate powder. This powder serves the purpose of both gain and scattering medium. Here the active medium is pumped by short pulses at a wavelength of 530 nanometer. The transition between spontaneous Raman scattering and stimulated emission can be quickly revealed by increasing the pump energy beyond a threshold. Here, conceptual drawing illustrate random Raman lasing that is built up from spontaneous Raman scattering. Several pump photons are shown entering the medium. One undergoes a spontaneous Raman scattering, whereas the other two are simply elastically scattered. The additional Raman photon is created via stimulated Raman scattering between two elastically scattered pump photon and the Raman photon. This is the mechanism that drives the Raman random lasing. Here the output Raman pulse energy versus incident pump pulse energy is plotted that indicates a clear threshold behavior where random Raman lasing begins. This figure shows the emission spectrum, stimulated Raman spectrum of barium sulfate powder at various pump power, illustrating the presence of higher order Raman transition. Other example of random lasing are micron size random lasing by the group of Huikau and a 2D random laser by using a zinc oxide nanoparticles. Zinc oxide is favored because it emits in UV where it is difficult to make mirrors. So in this context, mirrorless random lasers are alternative for laser at those wavelength. Random lasing is cold atom gas. Random lasing using opals and photonic glass infiltrated with dyes. Random lasing is also demonstrated in photonic crystal with intrinsic disorder. Now I will talk about possible future application of random laser. One of the possible application of random laser is to use it for pH sensing in the biomaterial. Here random laser system is fabricated using inverse silk photonic glass embedded with dye. The pH of the water solution surrounding the laser is controlled by varying the concentration of sodium hydroxide. The porous structure of the inverse photonic glass and permeability of the silk allow for the molecule to be efficiently affected by the solution. This figure shows the exact difference in spectra under neutral and alkaline pH environment. Here light multiply scattered in the gain medium embedded in the photonic glass leads to amplification and lasing shown by this red plot. The result is experimentally visible in the emission spectrum. For alkaline pH, the lasing emission is switched off, resulting in broadband fluorescence emission and then lower intensity. This is clearly visible in this orange plot. Here the intensity has gone down and then the width of the spectrum has increased. That means the system is now below threshold in an alkaline environment. So here the random lasing system is pumped above lasing threshold and emission characteristics as a function of the pH value are recorded that are corresponding to a strong decrease of peak intensity and sharp increase in the full width half maxima of the emission spectrum. This work has demonstrated that random laser based pH sensors are far better than conventional fluorescence sensors. Recently we have demonstrated temperature controlled spectral tunability of a partially pumped single wavelength random laser in our random lasing in our solid state random laser that is based on DCM doped PMMA layer. I have already explained this solid state random laser in previously slides. By carefully shaping the spatial profile of the pump, We first achieved a low threshold single mode lasing by using iterative optimization, and we have confirmed that this single mode lasing with high side lobe rejections. After that, we observed temperature induced changes in the refractive index of PMMA layer that results in blue shift of this single lasing mode. The temperature sensitivity of the emission spectrum in such a random laser can find application in temperature sensors. Speckle-free bioimaging is a potential application of paramount importance. Two vital features of random lasers are brightness and low coherence. Due to these properties, speckleless imaging is possible. In the case of conventional laser, interference pattern constructed between several wavefronts occur due to their high coherence. This gives us images that contain speckle, whereas other low coherence light sources like LEDs, they have very low number of photons per coherence volume. So to obtain high resolution single shot images with uniform background and low speckle noise, a low spatial coherence pulse source is developed, that is, and based on the random lasing effect. The bright low coherence narrowband illumination source can acquire high quality speckle free images and providing at the same time information on the amplitude and phase of the object. This illumination method significantly increases the image dynamic range and signal to noise ratio, which allow us to take full advantage of optical resolution of the microscope with time resolution. Other possible application of random lasers are random lasers can be used as a dopamine sensor, and a random laser can be used in photodynamic therapy. Drugs are initially attached to the target cell and after that they are activated via a random lasing light source. One of the features of a random laser is that it is a multi-directional. This advantage can be used in display technologies. The display panel can be coated using thin film of disordered media and doped with emitters. Random laser can also be used for tumor diagnosis as well. Random lasers are still a growing field and there are more to explore. Apart from such a laser complexities, the main challenge for the development of future application is the electrical excitation of random laser, which is important for display and lighting technology. Another challenging task will include developing innovative technology to control the directionality emission of the random laser, and for this purpose innovative directional confinement component may be introduced into the random lasing systems. In the end, I will say that the field of random laser is still in progress. While some random lasers are derived from classical lasing theory, the design and their fabrication are totally different. The light scattering characteristics showing random lasing makes the light-matter interaction more efficient. This results in much better lasing performance while coupled to classical resonator. It is clear that random lasing concept will provide new opportunities for photonic architecture and devices, and this can be fabricated using bottom-up as well as top-down approaches. The selective light scattering observed in many biological systems is often inspiration for future random laser construction and medical diagnosis. Polymers, due to their easily tailored physiochemical properties, are promising material for further development of low-cost and tunable random lasing devices. Thank you. If you have any question, please feel free to write me on the email address given in this slide.